Caitlin, how was Disney? Good. Did you have a favorite part?
We waited in like a 3-hour-long line for this like Avatar simulation ride, but it was like
totally worth it.
Ride ever. Yeah, it was totally worth it.
Good.
This is Valerie. She won another scholarship over the weekend.
Don't you have 2 or so many up to this point?
She already has full tuition. Now she just got another one.
Chatham?
Yeah.
Where's that located?
Like kind of like right by Pitt. Like it's in Pittsburgh. It's off of Fifth Avenue.
Oh, see, I always get that and Carlo mixed
Yeah,
up.
I know. That's what. Yeah, a lot of people. They're like they're in really like similar locations too. It's like Chatham, Carlo, and Pitt are like kind of like all in like a row.
Gotcha. All right. Well, congrats.
Thank you.
All right. So today we're going to start the second to last section. So you know how the first 2 sections we covered were related. Those were the parametric and the vector sections. These last 2 sections are related. We're going to talk about polar graphs, which I think are kind of cool, and then polar area. You know how you're used to area under a curve from Calc 1? We're going to talk about polar area, how it's slightly similar but yet different. Okay. So polar graphs, they're really interesting. I just wanted to kind of, I wrote down some different paragraphs here just so we can get a feel for how these polar graphs work. Polar graphs are different than a rectangular system, like with x's and y's. Normally, on a rectangular system, we would go out an x distance and then up a y distance to get to a particular point. Polar graphs or functions work a little bit different. Instead of a linear motion like right so much and up so much, we're going to do some rotating, meaning we have some type of angle to consider. So polar coordinates, I want you to imagine like you're standing at the pole, okay, which is kind of like the origin, and you're looking this way. You know how on a unit circle, this is kind of your starting side or your initial side, okay? So I want you to imagine that you're standing at the pole and you're looking out that way, okay? And you wanted to eventually get to this spot right there. How this works is if you're standing here, you're going to rotate a certain angle. So for instance, let's say I'm standing and looking this way. I'm going to rotate a certain angle because now I'm looking this way instead of this way. And then once I have that correct angle, I'm going to walk out a certain distance. Okay? So it's not just an x distance and a y distance. You have some type of angle or theta that you're going to rotate, and then you're going to walk out what's referred to as some radius of a circle. Okay, so we don't really have x's and y's in a traditional sense. We're going to have an angle and a radius. So what's also a little bit different is in a rectangular system, we write x comma y, and we're used to x being the independent variable. But in a polar example or a polar graph, the theta is your independent variable. And notice how that's written secondly, not first, like an x is. So this point right here, perhaps we'll say has this ordered pair to it, where the pi over 4 is the angle that you rotated, and the 4 is the radius that you've walked out. So polar coordinates, you're going to have some type of angle of rotation and then a radius or distance out from the center or that pole. Do we kind of see how that operates? All right. Now, what we can do is perhaps figure out some equivalent ordered pairs that would get us to this point. In a rectangular system, you only have one x and one y. But in a polar system, you might have more than one angle or more than one radius that would make sense. For instance, again, if I start here, remember my goal is to get over there, what if I rotated negatively wouldn't I have to walk backwards to get over there? Okay, so we could have more than one ordered pair that can get us to the same spot. And we're going to try to figure out what are some of those other equivalent polar coordinates. So let's see, instead of rotating pi over 4 and then walking out 4, can we think of another angle perhaps and another radius? Okay, so if you rotated, so you're standing here looking this way. If you rotate 5 pi over 4, you're now looking this way. Remember, you're still standing here, but you're looking this way. All right, so if you're standing here looking this way, you'd have to walk backwards to get to that spot. So your radius would be negative. Good. Let's see if we can figure out another one. Okay. So you are standing at the pole, looking this way. If you rotate backwards, so you're standing here, looking this way, and you'd have to walk backwards. So you had a negative rotation, and you'd have to walk backwards again. Can we get another one? There's actually 4 different coordinates that you can have for any polar location.
4, -7 pi over 4.
All right, so we're standing at the center, or the pole, looking to the right. If we rotate negatively 7 pi over 4, we are still standing at the pole, looking this way, and to get to where we want to go, we just have to walk out 4 units because we're already looking at where we want to go. So we got to be kind of familiar with radian values in terms of your unit circle, either positively or negatively. That way we can get to the correct location. Are we okay so far? We understand how a polar graph operates, how we can get to a point? All right, so there's some other things that we can do to help us figure out maybe the rectangular coordinates. So these are polar coordinates, but let's try to figure out what is the x distance and the y distance that we would have to travel if this was a typical coordinate plane. And in doing so, maybe we can use kind of a right triangle to help us analyze that. So we're going to go ahead and draw this triangle down here. So we're going to try to figure out the x-coordinate, the y-coordinate. If the radius was 4, we know that's kind of the hypotenuse of this triangle. And the theta value that we walked out, or rotated rather, was pi over 4. How can we figure out the x-coordinate and the y-coordinate? Yeah? Good. Okay, so we kind of have this pi over 4 location on the unit circle. So we're going to go ahead and try to figure out that special ordered pair if this was the unit circle. Maybe you want to kind of draw that in. But we can use some trig. So for instance, if we took the sine of that angle, we would need the opposite side, which was y, over the hypotenuse, which was 4. So using that unit circle, sine of pi over 4 was square root of 2 over 2. And like Eric said, we're going to have some factor of that or some multiple of that. We'd have to multiply the 4 over, which would essentially cancel out the 2 down below, and we'd have a 2 left over. So the y-coordinate is 2 square roots of 2. If we did cosine the same way, cosine would be the adjacent x over the hypotenuse of 4, but cosine of square or pi over 4 is the same square root of 2 over 2. So it looks like we'll get the same x coordinate as well. Okay, so we can use some kind of right angle trig or right triangle trig to help us with that. This is going to lead us into some general formulas that we're going to have to be familiar with. I can generalize this particular example as the sine of some angle of rotation, whatever it is, would be the y-coordinate over the radius, which in our example was 4. But if I were to ignore the pi over 4 and ignore the radius of 4, I can just substitute those with pi and r. Notice how I could probably solve this for y, and I get y equals r sine of theta. That's going to be a little shortcut for us in these next two sections. So if we're trying to figure out a y-coordinate, we can simply take the radius times the sine value of that angle. Similarly, for cosine, we could say the cosine of our angle was the x-coordinate over the radius, and then solving for x, we get r cosine of the angle. Are we okay with those two? Where those come from? Just using a right triangle? Okay. So the whole point that we're going to study these polar curves or polar graphs is because it gives us a way to graph, I don't want to say functions because they're not functions, but graph really cool equations. You notice how, or if you remember, how parametric equations were a way for us to graph equations that weren't functions. Remember how the first one I think we graphed looked something like that for our parametric sections? These polar graphs are going to look really cool, and that's what we're basically going to take a look at today. What type of graphs we can develop with these polar equations. So let's go ahead and take a look at some of the ones on the back. We're going to graph probably the first one or two together, and then we'll kind of see a pattern. Perhaps we can figure out what the rest would look like, or we can use the calculator to help us with some of the other ones. So what I want to try to do is, just for this first example, we're going to create a table of values. We'll do a theta and then the radius. So what we're going to do is we're going to use some easy theta values or radian values from the unit circle. We'll do 0, pi over 2, pi, 3 pi over 2, and then 2 pi. So if we were to plug 0 into cosine, cosine of 0 would be 1. Actually, let's go ahead and we'll use the pi over 4 also, just because that ordered pair is pretty easy. We'll use the other easy ones, not necessarily the over 4 values. What about cosine of pi over 4? From the unit circle, that would be square root of 2 over 2. Cosine of pi over 2 is 0. Cosine of pi is -1. 3 pi over 2 would be 0, and then we're back at 1 again. Okay, so with that ordered, or with that table, we're going to try to graph what this polar equation might look like. So remember, you're starting with the angle, and then the radius is telling you how much you have to walk out. So we're going to start at the pole, and we're looking to the right. If we don't rotate at all, because our angle would be 0, we'd have to walk out 1 unit. So if we start with the pole, looking to the right, walk out 1 unit, we would be right there. For the next set, we're at the pole, looking to the right, but then we have to rotate an angle of pi over 4. So we're kind of cutting this coordinate or quadrant in half. Okay, so we're looking this way. And then we have to walk out a distance of square root of 2 over 2. Maybe we'll say it's right there. For the next one, we're going to look up at pi over 2, but then we don't walk out at all. So even though we're looking up, we're still just standing at the pole or the origin. For the next one, we're going to look out at the pi direction, but then we have to walk a radius of -1. Where do you think we're going to land for that one? 0, I mean right here.
Or, sorry, -1, 0.
We're going to end. Okay, so we're standing here. We're looking to the left, but we have to walk a radius of -1, meaning walking backwards. So we're actually going to land at this beginning spot that we just had, right? For the next one, we're going to look down at 3 pi over 2, but we don't walk out it at all because the radius was 0. And for the last one, we're going to look out at 2 pi, and we have to walk out a radius of 1, so we're going to be back to where we started right there. Now I know we skipped some values, so there should be more dots on here, but if we were to connect the dots, it would actually create kind of a little circle in there. Notice how that circle, let's see, has a diameter of 1. We go from the pole to this outer edge. Can we try to take a guess about what the next one would look like if we did r equals 2 cosine of theta? What do you think the diameter might be on this one? 2 times, right? Because we're just doubling all of these r values from our table. So we're still starting at the pole or that origin, but we're going to double all of the radius distances. Let's see, the next one we can probably estimate or guess a diameter of 3. What about the last one? So instead of having a radius of 3 to the right, we're going to have that r value of 3 to the left, -3. Good. All right, now let's see if we can try to think about how these graphs would change if we had a sine function in there instead of a cosine. Can we take a guess? Educated guess? Kind of, right? Notice how cosine, all of these circles were drawn through the x-axis, because doesn't cosine represent kind of an x value on a rectangular system? So the sines are essentially y values. So all of our circles are going to be drawn through the y-axis. So this one should have a diameter of 1, but on the y-axis. And the next one has a diameter of 2 on the y-axis. And then 3. And then the last one will be -3. All right, so maybe as a reference, we'll say if we have some equations that look like r equals perhaps a times cosine theta, or r equals a times sine theta, we notice that a represents the diameter, and perhaps we'll say, and the trig function determines the axis. So if it's a cosine function, we know it should be drawn on the x-axis. If it's a sine function, it should be drawn on the y-axis. We doing okay so far? Those are really simple polar equations. We're going to see ones that kind of look a little more involved, or pretty even. Okay? So let's go ahead and amp it up. We'll take a look at some of the ones on the next page. So now, instead of just having like 2 cosine or 3 sine, we're throwing in a plus value in there. So let's see how that changes. Now for these, we're going to go ahead and utilize our calculator. Because creating a table of values might be a little cumbersome and take some time, we're going to go ahead and take a look at how this will help us go a little quicker. So what we need to do first is go to the mode button. And if you look in that 4th row, we talked about parametric equations, how you can change it to par. The next one is POL for polar. So I want you to go ahead and select that. Then I want you to hit the y equals button. Notice how all of those say r. If it's in function mode, they say y. If it's in parametric mode, you have the x and the y, but now that we're in polar mode, we have r's, because those are the radius. So we're going to go ahead and type in our first one, 2 plus 2 cosine. And notice how when you hit the x button, it actually comes up as theta. Before we hit graph, let's go ahead to the window. Similar to parametrics, when we had those t values to type in, we're going to have the theta values to type in here. Since we're talking about theta values, maybe we'll go from 0 to 2 pi, like a full circle. And then you can choose whatever step you want to. Maybe you want to count by 0.1s or 0.1. And then you can set the rectangular coordinates, how far you want to go on the left and the right. Maybe we'll do -5, or let's do -4 and +4, just because that's what we have on our paper. And we'll count by 1s. All right, so when you have it set, you can go ahead and hit graph. Did we get that heart looking shape? Yeah? So what we're going to try to do is draw that as best we can on here. If you hit the trace button, notice how it'll come up as the rectangular coordinate, but it'll also tell you the angle at which you're using for that ordered pair. And you may have to move kind of left and your right keys to help you move that cursor. So if you want to go ahead and plot some points, you can, or maybe you just want to draw a rough sketch. Looks like we definitely go through the pole, and then the rightmost point, I think, has a value of 4. So this shape is pretty special for these polar graphs. This is what's referred to as a cardioid. Can you guess why? It looks like a heart. Yep, like cardiac, cardioid. It's referencing a heart. Let's try the next one. Okay, so y equals we'll do 1 plus 2 cosine. So this one's a little different. It's not exactly a heart shape, but it looks like we have this inner kind of loop, and the inner loop goes out to 1, whereas the larger loop goes out to 3. Let's try the next one. 2 plus 1 cosine. That one doesn't have a loop, but it doesn't go through the pole either. Looks like we go out to -1 and then 3. All right, so something special is going on here with all these different equations. They're all similar. We have some number plus some multiple of cosine, but notice how depending on what those numbers or multiples of cosine are, we can potentially get 3 different graphical shapes. And this is what we're going to try to talk about in reference what these numbers represent in this type of polar coordinate format. So we're going to discuss what's referred to as the larger radius, and then the smaller radius. So in the first example, if we were to take the value of 2 plus the multiple of cosine, which is also 2, notice how we would get 4. But if we were to take the first 2 minus the multiple of cosine, which was another 2, we would get 0. So that's just for this first example. Remember, you're always starting at the pole or at the origin. So if you're starting at the pole, this largest radius is telling us how far we're going to walk out to the right. Looks like that would be a radius of 4. And then the smaller radius is telling us how far we would walk out to the left. And notice how that's 0. So we're not going to walk out at all. So the larger radius is 4 from that origin. The smaller radius is 0, meaning we're on the origin. And somehow, if we were to create a table of values out of all of these different methods or angles that we can kind of rotate towards, we would eventually get this heart-shaped graph. Are we experimenting? So
Yeah.
some of them can look pretty cool.
Pretty crazy.
Oh, I know. We're going to get there.
I don't know how you get that.
We're going to get there. Notice the next one. If we did 1 plus 2, the larger radius was 3, and that's how far we are to the right. If we did 1 minus 2, that would be -1, but that's telling us how far we walk to the left. But if you're walking -1 to the left, you're actually walking 1 to the right, and that's why we have this other kind of inner circle here. Instead of walking 1 to the left, we walked 1 to the right, so we have a smaller circle with a radius of 1 and a larger circle with a radius of 3. For the last one, if we did 2 plus 1, that would give us the radius of 3 to the right. If we did 2 minus 1, we would get the radius to the left. And connecting those, we would just have a simple circle. So sometimes we have a heart shape, sometimes we have an inner circle, sometimes we just have one big circle. It all depends on the relationship between the number being added and the multiple of cosine. Do we kind of see that happening? Can we take a guess about how these ones would be similar if we change cosine to sine? They're going to be on the y-axis, yep. So if we did 2 plus 2, the outer radius, in this case going up, would be 4. 2 minus 2, the radius to the, I guess, down in this case would be 0. and we're going to create some cardioid shape again. For the next one, 1 plus 2 would be an up radius of 3. 1 minus 2 would be a down radius of -1, which means we'd actually be going up. So we're going to have some inner loop. Actually, this shape is what's called, and I can never pronounce this right. Maybe those of you that know French can help. And I don't even know if I'm going to write it right. Is it limacon? 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 I don't know. No, that's not it. Do you know what that means in French? No? It means snail. And I guess the reason they call that is because this shape resembles the shell of a snail. So the heart shape is a cardioid, snail shape is limacon, or however you pronounce it. Let's see, the last one, if we did 2 plus 1, we have an up radius of 3. 2 minus 1 is a down radius of 1. We'll have just one circle. Okay? That's basically it for those ones. We talked about all of these different questions as we went through the examples. Let's try some more. All right, so on your calculator, we'll go ahead and type in 3 cosine of 3 theta. All right, so if we tried to draw this one, it looks like the loop on the right goes out to 3. And then we have 2 other loops, one in the second quadrant and another one in the third quadrant. Let's try the next one. 2 cosine of 5 theta. Let's see, this one looks like it only goes out to 2 on the x-axis, and then we have 4 other petals. And the last one, 4 cosine 7 theta. Alright, so this petal on the right goes out to 4, and looks like we got 6 more. Alright, before we try the sign ones, can we find some connection, perhaps, between the equation and, we'll call it a flower, the flower that we develop? What do you think, Cameron?
The number out front is the radius, and then the number inside the theta is the number of the petals.
The petals. Okay, so this is your radius or the length of the petal. If you're talking radius, it'd be how much you have to walk out. In this case, the length of the petal. And then the number on the inside is the number of petals. So if we check it out, this one, we should have petals that go out 2 units and 5 of them. And then we should have a petal of length 4 and 7 of them. Looks like it checks out. How do you think these would change if we changed it to sine? It's on the y-axis. So notice how for all of these, the starting petal was on the x-axis, okay, on the right side. So for the sine ones, they're going to be on the y-axis. But do you think it's going to be on the top or the bottom? This is what's a little tricky. Let's try 3 sine of 3 theta. Notice how this one's on the bottom. Still a length of 3, and we still have 3 petals though. If we tried the next one, 2 sine of 5 theta, this one looks like it's up top. So the sine ones can be a little trickier. Some of them can be up top, some of them start down below. I feel like I just drew Patrick from SpongeBob right there. Let's see, the last one. 4 sine, 7 theta. Looks like we start down below too. We doing okay?
I'm just really bad at drawing.
Oh, me too. Me too. It's just a rough shape, okay? Just like the length of the petals and how many petals you have might be the best. All right, let's try these ones down here. 3 cosine of 2 theta. Before we hit graph, I know some of you may have already done it. Before you hit graph, can we think about how many petals we should have and the length of them? Based off the other examples we did at the top. We would have 2 petals of length 3, right? If it followed the same pattern. But not quite. Okay, so look, this one looks like we have 4 petals of length 3. And what's neat is all of the petals happen to be on an axis, or axis. How many petals are you trying to draw? All right. I think we're going to stop there because the bell's going to ring in a little bit and you guys are having too much fun graphing these on your own.
This is too fun.